Welcome back to AI Foundation Learning. Today, we're diving into the fascinating world of agentic AI. Ever wondered how systems like autonomous vehicles, virtual assistants, or intelligent game agents are built? Well, you're in the right place. In this video, we'll break down the core components and architecture required to build an agentic AI system. Whether you're new to AI, an enthusiast, or a seasoned professional, this video will guide you through the key concepts and architectural considerations for creating autonomous agents. We'll also showcase the latest tools and techniques used in the industry today. So, let's get started. Agentic AI systems, or autonomous agents, are software entities that can perform tasks on their own without constant human intervention. These agents perceive their environment, make decisions, and take actions to achieve specific goals. Think of an autonomous vehicle navigating through traffic, a virtual assistant scheduling your meetings, or a game AI opponent that adapts to your playstyle. These are all examples of agentic AI. But what makes these systems tick? Let's explore the core components required to build such intelligent agents. To build an effective agentic AI system, you need to integrate several key components. Let's break them down one by one. The first component is perception, where the agent collects data from its environment. This could involve sensors like cameras and LiDAR for a robot, or APIs and databases for a software agent. Tools like OpenCV for computer vision or Google's Vision AI can help in building the perception layer. Once the data is collected, the next step is decision-making. This involves analyzing the data to determine the best course of action. Decision-making can be rule-based, driven by machine learning models, LLMs, or a combination of both. For example, reinforcement learning frameworks like OpenAI Gym or Google's DeepMind can be used to train agents to make intelligent decisions. Planning is the component that allows the agent to figure out how to achieve its goals. This could involve pathfinding algorithms for navigation or scheduling algorithms for task management. Tools like Google or Tools or ROS, Robot Operating System, are often used for planning in robotics and other autonomous systems. Finally, the agent needs to act on its decisions. This involves sending commands to actuators in robots or executing functions in software agents. In robotics, libraries like ROS or PyBullet can be used to control and simulate physical actions. In virtual assistants, APIs and natural language processing tools like Dialogflow or GPT models are used to execute actions. These components work together to form the backbone of any agentic AI system. But how do you integrate them into a cohesive architecture? That's where architectural considerations come into play. Designing an agentic AI system requires careful architectural planning to ensure that all components work seamlessly together. Let's explore some of the key architectural considerations. Modularity. A modular architecture is essential for building scalable and maintainable AI systems. By separating the perception, decision-making, planning, and action components into distinct modules, you can easily update or replace parts of the system without affecting the entire architecture. For example, you might use TensorFlow or PyTorch for decision-making, but switch to a different framework as needed without changing the entire system. Interoperability. Interoperability between different components is crucial. This involves choosing the right communication protocols and data formats to ensure that all modules can exchange information efficiently. In robotics, ROS is often used as a middleware to facilitate communication between sensors, processors, and actuators. Real-time processing. For many agentic AI systems, especially those operating in dynamic environments like autonomous vehicles, real-time processing is a must. This requires optimizing your algorithms and choosing the right hardware, such as TPUs or GPUs, to ensure that the system can make decisions and take actions in real time. Learning and adaptation. An effective agent should be capable of learning from its environment and adapting its behavior over time. Reinforcement learning and continuous learning frameworks are often integrated into the system's architecture to allow the agent to improve its performance as it interacts with the environment. Safety and ethics. Finally, when designing autonomous agents, it's crucial to consider safety and ethical implications. This includes implementing fail-safes, ensuring transparency in decision-making processes, and complying with regulations. Techniques like explainable AI, XAI, can be used to make the agent's decisions more interpretable and accountable. By considering these architectural aspects, you can build agentic AI systems that are not only functional but also reliable, scalable, and safe. Large language models, or LLMs, like GPT-4, are transforming the capabilities of agentic AI systems. These models bring human-like understanding and communication skills to AI agents, enabling a new level of autonomy and effectiveness. First, LLMs enhance perception and understanding. They allow AI agents to comprehend natural language instructions, interpret complex information, and grasp the nuances of human communication. Second, they bolster decision-making. With access to vast knowledge, LLMs help agents evaluate options and make informed choices, even in uncertain situations. Third, LLMs enable continuous learning and adaptation. Agents can update their understanding in real time through natural language inputs, adjusting their behavior based on new information. Lastly, they improve human-AI interaction. With advanced language capabilities, AI agents can engage in more natural and intuitive conversations with users. By integrating LLMs, agentic AI systems become more intelligent, adaptable, and aligned with our needs. This synergy is paving the way for innovative applications that enhance our daily lives, from smart assistants and customer service bots to advanced robotics. In essence, large language models are the catalysts propelling agentic AI systems forward. They empower AI with the ability to understand, decide, learn, and interact in ways that were once thought impossible. As we continue to harness this technology, we're witnessing the dawn of a new era in AI innovation. Let's put all these concepts together with a practical example: building a virtual assistant. Here's how you can apply the key components and architectural principles we've discussed. Perception. The virtual assistant uses natural language processing tools like Google's Dialogflow or OpenAI's GPT to understand user inputs. Decision-making. A machine learning model is used to interpret the user's intent and decide on the appropriate response. You might use pre-trained models or fine-tune a model using your own dataset. Planning. The assistant plans its response by considering context, user history, and available actions. For instance, if the user asks to schedule a meeting, the assistant checks the calendar and suggests suitable times. Action execution. Finally, the assistant executes the action, such as sending a meeting invite or providing a response to the user. This involves API calls or triggering predefined workflows. By following this structured approach, you can build a virtual assistant that effectively understands and responds to user needs, all while being scalable and adaptable. As we've seen today, building an agentic AI involves integrating several key components and carefully considering the overall architecture. With the latest tools and techniques, from reinforcement learning frameworks to modular architectures, the possibilities for creating intelligent, autonomous agents are endless. If you found this video insightful, be sure to give it a thumbs up and subscribe to AI Foundation Learning for more deep dives into the world of AI. And don't forget to hit the bell icon so you never miss an update. Thanks for watching, and see you in the next video.